So in this video from today, we're going to be looking in more detail at successive ionisation energies. That's removing electrons from a single atom all the way down to the nucleus. And we're going to have a look at what that tells us about the principal quantum shell structure. So we're going to look at two processes. First of all, we're going to look at the loss of all the electrons from one atom, and that's going to give us evidence for these principal quantum shells. Then we're going to move on to look at the loss of one electron from successive atoms in the periodic table, and that's going to provide us with evidence for subshells. So the successive ionisation energies is the energy required to remove an electron one by one from the same atom. Now that's going to depend on three things. Firstly, the number of protons. Well, as we're dealing with the same atom, that number is not going to change. It is also affected by the screening effect of completed inner shells of electrons. So those complete inner shells, they screen the outer shell electron from the nucleus. And last but not least, we're going to look at the distance of the electron from the nucleus. So we're going to look at the graph for sodium. So we've got a logarithmic ionisation energies up the side. We use a logarithmic scale because the values are too large otherwise to see the relationship. And we've got the number of ionisations, so the electrons being removed. So the first electron we can see here is in principal quantum shell 3. It's quite easy to remove because it's reasonably far from the nucleus and it's screened by these inner shell electrons. There's a big jump to the next electron because we're moving in a principal quantum shell. That principal quantum shell is closer to the nucleus and it's lost its first shield. So now it's only being shielded by these s electrons here. So we get this gradual increase as we're removing an electron from an increasingly more positively charged ion. We get another big jump to the last two electrons to be removed. They are much closer to the nucleus. There's no shielding now, so they're very hard to remove. So here's the first electron I'm removing. Then I remove these 8 and then the last 2. So those electrons are being removed from a shell closer to the nucleus. It's what we call a lower energy level, and it requires more energy therefore to remove them. They've lost shielding and they're closer to the nucleus, so it's harder to remove them. You get that gradual increase because you're trying to remove an electron from an increasingly more positively charged ion, and that's going to be harder to do. And we use a logarithmic scale to provide us with a better pattern, so we can enable us to see the patterns that are developing. So what we'd like you to do now is to practice this using the data on page 14. So you're going to need to plot a graph of the successive ionisation energies of calcium versus the electrons being removed. So here we have the plot of the calcium's ionisation energies, the successive ionisation energies. And you can see the first two electrons, again, quite easy to remove. You've got the jump to the next electrons, you've got that gradual increase before the jump to the next principal quantum shell, again, gradual increase before a jump to the last 2 electrons. So I've plotted the logarithmic scale versus the number of electrons being removed. And you can see the same pattern that we saw for sodium. The jumps coming between the principal quantum shells. So now we're going to move on and look at the first ionisation energy for successive elements. And this is giving us evidence for these subshells. So again, we have these 3 things which impact on our ionisation energies: proton number, shielding, and the size of the original atom, so the atomic radii. So as you increase the proton number, the ionisation energy increases. There's greater attraction of the electrons to the positive nuclear charge. More shielding, on the other hand, will decrease the ionisation energies. As more inner shells get filled up, there's less attraction of the electrons to the positive nuclear charge. And last but not least, How we expect it to change with size? Well, as the ionic or the atomic radius increases, then the HI decreases. Obviously, if you're dealing with an atom, it's atomic radius. If you're dealing with an ion, it's the ionic radius. So as we have more protons, we have an increased energy required to remove the electron because they're held closer and tighter by the nucleus. If you increase the shielding, there's less attraction as the electron you're trying to remove is shielded by these full inner shells. And lastly, as you increase the size of the atom, there's less attraction as the electron you're trying to remove is further away from the nucleus. So again, there's less electrostatic attraction. So I've got there my table of atomic radii and first ionization energies. One of the first things that you should notice is that the atomic radii decreases as you go across a period, if we ignore the noble gases. And the reason for this is you're adding an extra proton to your nucleus each time. The electrons are going into the same principal quantum shell. They have the same roughly amount of shielding. So those electrons are being pulled closer to the nucleus by having that extra electron. As you go down the group, the atomic radii increases because we're now adding a whole nother shell of electrons which is further from the nucleus and more shielded. So that size increases. And that's the key reason, or one of the key reasons, why the ionization energy decreases. So as you go across, there's a general increase. There's a general increase because your proton number is increasing, your shielding remains roughly constant, they become a smaller atom, so it becomes harder to remove the electron. So as you go down that group, yes, the proton number increases, but you've got a complete inner shell of electrons, so shielding and radius increases, and hence the HI decreases. So that's the general trends for both going across a period and down a group. But you might have spotted there are a couple of discontinuities. In other words, changes to this general pattern. So for example, between beryllium and boron, the ionization energy goes down. The same for magnesium and aluminium. There's also a bit of a blip between nitrogen and oxygen, and phosphorus and sulfur. So in both cases, the ionization energies go down, even though the atomic radii goes down, so you expect it to become harder to remove the electron, and the proton number goes up. And we're going to look at that in the next couple of pages. So our general trend as we move across a period is always an increase, and then we drop back down as we change periods. So the group with the highest ionization energy is always these. It's always the noble gases, and you can see those there. The group with the lowest ionization energies are always group 1 because of the first element of a new period. Now there are these blips we talked about. So there's a blip, another blip there, blip and blip. So they're these minor changes. They're not as big as the change between whole principal quantum shells, but they are bucking the trend. They are going down when we'd expect them to go up. And this was the key piece of evidence that led to the existence of subshells. So to understand this, we need to look at the electron configuration of beryllium and boron. So beryllium, 1s2, 2s2. Boron, 1s2, 2s2, 2p1. So boron's first electron is coming from a 2p subshell. Now it's still closer to the nucleus and it's still got more protons than beryllium, but it's in a higher energy level. It's in a 2p rather than a 2s. Also, the 2p electron is being shielded or screened by these 2s electrons. And that's enough to reduce the ionization energy by a small amount. We have the same argument for magnesium and aluminium. So magnesium has this electron configuration, aluminium has its last or valence shell electron in a 3p orbital. Consequently, the p orbital is, or the p electron is slightly shielded by the 3s. The aluminium electron is in a slightly higher energy level, so it's slightly easier to remove. But we also need to consider the blip between nitrogen and oxygen. This time I need to look at their electron configuration in the boxes. So I have 1s2, 2s2, 2p. So I have 2 electrons in my 1s, 2 electrons in my 2p, and then I have 1 electron in each of my p orbitals. Oxygen, I have 2 electrons in my 1s, 2 in my 2s, but this time I have 1, 2, 3, 4 electrons in my 2p. Now that first electron is slightly easier to remove than nitrogen's first electron because it's a paired electron, and paired electrons are going to be slightly easier to remove due to electron-electron repulsion. So that explains these little blips on the chart. This first blip is caused by the fact that you're going from an s subshell to a p subshell, and the p electrons are slightly shielded from the nucleus by the full s orbital, and also they're in a slightly higher energy level. These blips are caused by the fact that you've got unpaired electrons in each of the p orbitals for nitrogen, but when you move to oxygen you have a paired electron, and that paired electron is slightly easier to remove, and that's the same argument in period 3 here and here. So we're on page 17 of your notes, and we're just going to annotate this diagram. So firstly, there's this general increase as we're removing an electron from an increasingly more positively charged ion. Our 3 electrons in our outermost shell. There's a slight dip or a slight gap between the first and the second as we're removing an electron here from a p and here from an s. We've got the bigger jump here between the third and the fourth because we're removing an electron from a whole shell closer to the nucleus, and it's lost a level of shielding. There's again that general increase before we get the next big jump to an inner shell, less shielding, closer to the nucleus. And again, we've got those last 2 electrons to be removed. So I've got 3 electrons in my outer shell, and I've got a total of 13 electrons being removed. So this is the element aluminium. So it sometimes helps to write on which electron is being removed. So you're going from a 3p to a 3s, so there's a minor change there. So here you're jumping between a 3s and a 2p, so these are all my 2 electrons being removed, and then I've got a big jump again to the 1 principal quantum shell, so this is the shell closest to the nucleus. So within a period, the ionisation energy increases because we've got more protons, shielding stays roughly constant, but the radii, as you see, has decreased. There's a small decrease between beryllium and boron and magnesium and aluminium because you're removing a p electron, and that's being removed from a higher energy level, and it's being shielded by those full s subshell, and that makes it slightly easier to remove. Nitrogen, oxygen, and phosphor and sulfur, there you're removing a paired electron, and that's much easier to remove. Noble gases are at the peaks because they have the highest proton number of their period. They're also in the most stable electron configuration. Group 1 have the lowest because they've got a low proton number of the period, they've got the highest radii. So down a group, the ionisation energy decreases. That's because you're increasing your shielding and your radii, and you're removing an electron from a higher energy level, so from a shell further away from the nucleus. This is despite the fact that you've got that increased nuclear charge. So you can see there the trends. So as we go down, group 1, there's a decrease. As we go down, group 8, there's a decrease. There's a general increase until you hit the noble gases, and then everything kind of resets as we join the next period. We've got our little blips here, here. First blip is due to the existence of the p subshell, and the second blip is due to the paired electron effect. So that just finishes off this section looking at the ionisation energies. Do check over the front cover again and make sure you're happy with all those specification points. What we'd now like you to do is to have a go at the questions at the back of the pack and make sure you have it ready to be handed in. We will mark it and give it back to you with some comments. So until then, take care, stay safe, bye bye.